All right there, wonderful people. Here we are for our next podcast video. We're starting on Unit 2, which is Fundamentals of Radiation. We have two topics in this unit. Topic A is on the physics and characteristics of radiation. Now, thinking about the physics and characteristics of radiation, basically what that just means is, what does it look like? How is it physically impacting the world? So when we look at the definition of physics, is the study of the basic principles that govern the physical world around us. Remember, we talked about before taking a word and breaking it up into its prefix, suffix, and root word. Well, we're actually breaking it up, not down this time. Physics, thinking of the word physical world around us. This includes motion, forces, momentum, energy, and other concepts in lots of different physical situations. In this case, since we're talking about radiation, radiation is actually energy in motion. That's what it is in the most basic sense of the word. It's energy in motion, and that energy can be used for good or it can be harmful. Before we get started talking about it, I want to point out to you that there are some videos available on our website associated with various topics. I have some really good videos associated with this class in particular and this subject in particular that may help paint a picture for you prior to listening to the rest of this podcast. You will not be tested specifically on anything in these videos if I don't talk about it in the rest of the podcast. So don't watch these videos with the intention of having to memorize any of the terminology or words in them, but just watch them to get the overall concept of what radiation is. So if you go back to our website, toggle over from this video to our website on our homepage, and right at the top of our homepage, hover over the CE courses link, and then hover over the X-ray certification link, and the resources for radiation safety course link will show up. Click on that, and then you will get a page that looks like this. I neglected in the first couple of podcasts to talk to you about this resource for you, and so there are some miscellaneous links here that you might want to take a look at prior to delving into coming back to physics and characteristics, our unit 2. Overall, there's some website resources here. So remember, I mentioned to you there's a national board exam on radiation health and safety. Here's a link to Danby's RHS exam. So you can find out more about that exam on that website. This website here, Dr. Spiller's Radiation Safety Course, is a really good in-depth course online, and you can jump around from topic to topic in there and take a look at it. It has some great information in there, and I'll mention it periodically through the rest of the podcasts. One of the interesting and great parts of his website, there is some information on digital radiography. So if you want more information specifically on that, also on cone beam technology and CT scanning, there's some more information on those things there in those websites. For us today, here is our Unit 2, which is what we're on now, Topic A. And what I would watch right now before going back to this video is these two links right here. What is radiation and our radiation environment? If you go watch those two, and they're very short, they're like 4 or 5 minutes each, they're going to give you an overview of what we're talking about here. So you've got a concept, you've got a roadmap and a picture in your mind of what we're talking about before jumping back into the nitty-gritty of it. So I would do that right now. And then there's also an article here that you can read if you want to read that article. You certainly don't have to. Maybe take a look at it and see if it's something you want to spend time on. But definitely watch these two videos right here and then come back to me. All right, so hopefully now you have a picture or a concept of what radiation is. Hopefully you've learned something new about it, because we all have had preconceived ideas about it prior to, but maybe you've learned something new already, which would be wonderful. There are three harmful types of radiation. These three types of radiation are the three that are potentially harmful to human beings: X-rays, ultraviolet rays, and gamma rays. We come in contact with X-rays whenever we go to the dentist or have an X-ray done for some medical reason. Ultraviolet rays, of course, from the sun, we come in contact with all the time. Gamma rays are the most harmful rays, and hopefully we don't come in contact with those because those are super harmful. Now, some people do kind of talk about X-rays and gamma rays as if they're the same thing. They're really technically not the same thing, but they're on the same end of the spectrum of radiation, and we'll talk about that here in just a minute. In order to understand radiation, we have to break it all the way down to the very basic fundamental unit of matter, which is an atom. An atom is a molecule that has, and this is going to remind you of chemistry. Hopefully this is not brand new to you. You've heard this before. But again, an atom is the basic unit of matter that all atoms have three components to it. It has a positive component, which is a proton, a negative component, which is an electron, and then a neutral component has no energy, which is a neutron. The neutron and the protons are in the center of the atom, and electrons actually orbit around the outside of the heart of the atom. So in this case, it is referring, let me get rid of those, referring to a carbon atom. Carbon atom has 6 protons, 6 electrons, and 6 neutrons. So when an atom is balanced, it doesn't have any energy right now because it's balanced. Think if you have a positive 6 and a minus 6, then you get 0, which means it's stable. In order to have energy, we actually have to unbalance it. We have to give it more protons or more electrons. So actually where electricity comes from is taking the electrons off of an atom and using those negatively charged particles to create energy. The energy that we create when we do that, for our purposes, we turn it into radiation. So again, going back down, don't make this harder than it is. What you need to remember is an atom is the fundamental unit of matter. Every atom has 3 components: proton, electrons, and neutrons. If we have an equal amount of each, we have balance, no energy. In order to have energy, we have to unbalance it, which means we have to take some electrons off or protons off and make it unbalanced. Okay, when we do that, we have energy, and then we're going to use that energy for radiation. When we unbalance it, this is called ionization. Ionization is just the process of turning an atom into an ion. How do we do that? Again, we take either the protons or the electrons, normally the electrons, and do what we have to do to pull the electron off of the orbit. And so what we now have is this one atom that's not balanced. The electrons are over here, the protons are over here, and it is not a cohesive atom anymore. Doing that is creating an ion, or the ionization. Okay, at this point you might want to watch the video ionizing radiation back on our website, and scan or read the article "What is ionizing radiation?" and then come back. Okay, welcome back. Hopefully you got some good information there. Ionizing radiation is radiation that is harmful. If we look at this chart right here, it says the electromagnetic spectrum. One of the acronyms, I can say it, that you need to know is EMR, electromagnetic radiation, EMR. And spectrum just means a variety. So from one end to the other. And what are the two ends we're talking about here? Well, the two ends we're talking about here are the harmful end, or the harmful type of radiation, which is ionizing radiation over here. Whoop-a-daisy. Sorry. Ionizing radiation, all the way down to radiation that is not harmful. Notice that on this side, ionizing radiation, we have that is harmful. We have gamma rays or cosmic rays and X-rays. Also within the ionizing radiation, we have some ultraviolet rays, right? Rays from the sun. You can get skin cancer from the sun, and that's ionizing radiation. As we work down towards the non-ionizing type of radiation, it becomes less and less harmful, and in most cases is not harmful to us, to most human beings, unless there's extenuating circumstances. So that is microwaves, radio frequency spectrums that are like your cell phones, TV, radio, your computer monitors, and that kind of thing. Those are all types of radiation, but are not harmful to most of us. So what makes radiation harmful or not harmful? Well, its strength makes it harmful or not harmful. I like to use a lot of analogies, and sometimes they work and sometimes they don't, but if it helps, most people think that they help you in some way paint a picture. So let's say I throw a ball to you, and I'm going to use this ball analogy a couple times in this podcast. If I throw a baseball to you, if I throw it underhand and kind of lob it to you and you catch it, is it going to sting your hands? No, it probably won't sting your hands. When you catch it, you feel it in your hand, but it's not going to sting you. But if I use more velocity in throwing the ball to you and then you catch it, it is going to potentially be harmful, right? So same thing in your radiation. The stronger it is, the more penetrating power it has, the more harmful it is. So what causes that penetrating power of radiation? Well, radiation travels in a wave. It does not travel in a straight line. Well, I couldn't draw a straight line, but that was an attempt at a straight line. Radiation travels in waves. The faster the wave travels and the closer together the peaks are between each other, the more intensity the radiation has. So your short wavelength, high frequency, high energy radiation is what's going to be harmful. So short wave radiation is harmful. Long wave radiation is not harmful. And again, what we mean by that is when it travels in a wave, think of an ocean wave, from one wave to the next. The distance from one to the next, if it's far apart, it would be less harmful. If it's close together, it's going to be more harmful. Now, where that can be confusing is, for example, the sun. The sun, most of the sun's rays travel in long waves. They actually travel in both long and short. If we go back to our image that we just had a second ago, notice that our sunlight here is within both ionizing and non-ionizing radiation. So there is some waves, radiation waves from the sun, that travel at short wavelengths. The distance between the peaks is short. Notice as they get shorter and shorter and shorter, we're getting more and more harmful. As we're getting longer and longer and longer distance between the wave peaks, we're getting less and less harmful. So ionizing radiation breaks off right about here, that some wavelengths are short wave from the sun and some are longer wave. The ones that are short wave are the harmful ones. The ones that are longer wave radiation are not harmful. All right, stick with me here. We've just covered some interesting stuff. And we're going to throw a few new terms at you, but really that's the hardest part of this lecture that I just went over in the first 10 minutes or so. So let's go over the X-ray tube head now. So talking specifically about dental X-ray radiation. What do we mean by the tube head? Well, the tube head is the part of the X-ray machine that is right here. The radiation is actually produced in this part right here, and on a portable unit, it's within this housing right here. This part, oh, Melody, this part right here is, a lot of people call it the cone because it used to be cone shaped. I have some pictures of a cone shaped PID. The proper term for that is a PID, position indicating device. PID, position indicating device. Again, commonly called a cone. That's going to help you position the radiation to come out towards the patient's face. And then of course we have the arm and the control panel, which we already talked about, and we're going to talk about again here in a minute. The outer case of the X-ray head is made out of lead because lead is the type of metal that radiation cannot go through. Within that outer case, the tube head is made out of glass. It's the components inside are wrapped in glass, and it's a glass vacuum tube, meaning that all of the air has been sucked out of it in order to create the radiation on the inside. So there's a glass vacuum tube encased with a lead housing on the outside of your X-ray head so that the radiation only comes out the opening or portal where there is no lead, and that is where the radiation is going to come out and be aimed at your patient. So what we're going to do right now is we are going to draw the inside of the tube head, and I'm going to try to draw it here with my mouse in a couple of different colors for you, and then I'll show you some pictures of it. So get a piece of paper and maybe some different colored pens and pencils and draw this out, which will help you remember. Maybe flip over your worksheet that you're working on and draw it on the back side, and that will help you remember the components on the inside of the X-ray head. All right, so let's draw the tube head. So here's our tube head. Okay, we just drew this piece right here. And remember what I said, the outside of this is made out of what? Lead, right? The outside is made out of lead because that's the metal that radiation cannot go through. Right? Inside of that, we have a glass vacuum tube. So inside there, we have this glass vacuum tube. Okay? Now, there are two components inside the glass vacuum tube. There's one component over here, and there's a coil on the inside of that, and it's really hard to draw with my mouse, so excuse my terrible drawing here. And this side of the tube head is actually negatively charged. It's the negative side of the tube head, and that is called the cathode. C-A-T-H-O-D-E, cathode. Okay, the negative side of the tube head. On the other side of the tube head over here, we have the positive side. Now it's really important that you draw this positive side over here in the tube head with this angle right here at a slant, and I'll explain why in just a second. So make this angle at a slant. Like I said, this is the positive side of the tube head, and that is called the anode. Okay, that's called the anode. Cathode is negative, positive side is the anode. All right, now negative and positive, where did that come from? Do you remember just a couple minutes ago, hopefully you remember that we talked about an atom, right? And an atom has positive particles and negative particles. Remember, negative were electrons, positive particles are protons. So what we've done when we turned on the power button to your x-ray head, so first thing you do when you come into work in the morning, before you take an x-ray, you have to turn the unit on. By turning the unit on, you have created electricity and immediately pulled electrons off of atoms, and the electrons, because of the magnetic pole in the components that are in the x-ray head, the negative components have come over here to the cathode and the positive components have come over here to the anode. So we've split an atom and divided the negative and positive particles. Now what does that do? Remember I said if they're balanced, then we don't have any energy. Now we have a ton of energy because we have pulled the atoms apart and we have all of this negative energy on one side and all of this positive energy on the other side. So when we push the button, so negative side of course means that the electrons are sitting over here within this cathode. Electrons are over here. Now when we push the button, so we put the receptor in the patient's mouth and we push the button to take the x-rays, we release the electrons, okay, and the electrons then by magnetic pull come over and want to be reunited with the protons over on this side. Okay, somebody told me once to use the analogy of a middle school dance where you have all the girls on one side of the gym and all the boys on the other side of the gym, and they are both electrically charged, right? We have the negative on one side and the positive on the other side. And when we say go, or we turn the music on, one side starts to kind of migrate to the other, although they certainly don't go as fast as the electrons do here. But anyway, if that analogy works for you, go for it. Anyway, when you push the button to take the x-ray, you're releasing the electrons and the electrons automatically come over to the side. Now, do we want the electrons to actually engage with and connect with the protons on the positive side? We don't, because if we let them connect with and engage with them, then we lose the energy. So what we want is we actually put something in the way, and that something is a piece of metal that we put right here. We attach it to the outside of the anode so that when the electrons hit this piece of metal, and this piece of metal is made out of tungsten. Tungsten is a type of metal that has a very high melting point. You might have heard of a tungsten ring, like wedding rings seem to be popular now, made out of tungsten, and it doesn't change its shape. Anyway, it's a type of metal. So this piece right here is called the tungsten target. Important to remember that for a couple of reasons. So that piece of metal is called the tungsten target. Now remember, when the electrons hit that tungsten target, they're not reuniting with the protons, so we still have the energy. And what happens when the electrons hit that target? The ray that is produced is because of the angle of the target, the ray that is produced is X-rays. The proper name for that ray that is produced at this point is called photons. P-H-O-T-O-N-S, photons. Again, since we drew this in such a way that the tungsten target is angled, the angle of the photons are coming down towards the opening where we have an opening in the lead case. Now, once the rays go towards that lead case, or whoop, 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 whoop. How did that happen? That was kind of weird. Okay. Here we go. Once the rays go towards that opening, we don't want them to come out just as they are because they'd be way too strong. So what we have to do is put a couple things in the way that prevents them from being super strong. The couple things that we put in the way, first of all, one thing that we put there is an aluminum filter. That is a piece of aluminum that radiation can go through if the radiation is super strong, but your weaker radiation will stay within the X-ray head. Okay, so the aluminum filter allows only the strong radiation to go through. So it's like a filter, your coffee filter, right? It's letting the good coffee go through the filter and keeping the grounds from going through. The next thing we have is what's called a collimator. A collimator is like a lead washer. So make sure when you draw that, you draw it with an opening in the middle. If you think of a washer as kind of like a donut, right? When you have a nuts and washers, it's like a donut. And so this part here would be all made out of metal, and then you have a hole in the middle, right? That's what we have here on this side. So here's the hole in the middle, and it's made out of lead. Okay. So let me type this out. It's made out of lead. So where's the radiation able to come out? The radiation is only then able to come out of the hole right here. And the hole is made the right size for the length of the cone, or the PID, so that when the radiation comes out of that hole, it spreads out, and by the time it hits the end of your PID or your cone, the width right here is 2.75 inches, and that's something that you do need to remember. Okay, so the hole is the right diameter that allows the radiation to come through. So the radiation is restricted to this width of 2.75 inches. Now, when the radiation comes through, it's aimed at our patient, right? So when it's aimed at the patient and the receptor in the patient's mouth, it's going to hit the receptor in the patient's mouth. It's also going to hit the patient's face and tissues and so forth and bounce off. So remember I said a few minutes ago, we have that analogy of the ball, right? If I throw a ball, so imagine that radiation is a ball being thrown at the patient. When the patient does not catch it, because the patient's not going to catch all of the radiation, some of it bounces off. And what bounces off can come back and hurt you if you're standing within the danger zone, and the danger zone is 6 feet. Things and we'll be done here. Now the radiation, remember that ball, when you throw the ball at the patient and it hits the patient's face, teeth, tissues, whatever we're aiming at, and it bounces off, it's going to continue to bounce around until it loses its energy. So again, if you throw a ball against a wall and it bounces off and then it bounces around the room until it stops. These beams of radiation, and we call them beams, all have a different name. The beam that is aimed at the patient is the useful beam. It's the beam that's going to expose the receptor and put the image on the receptor, and that is called the main or primary beam. It's also called the central ray. So it has a couple of different names. Central ray, main beam, or primary beam is the ray aimed at the patient. The ray that bounces off of the patient and then bounces around, so directly off of the patient, is called the secondary radiation, because we called the first one primary, so this one is now secondary radiation. And then the radiation that bounces around until it stops bouncing around, it loses its energy, that is called scatter radiation. Okay. And then there's one more type of radiation, and that radiation is called leakage radiation. And leakage radiation is from a cone, this PID, that may not be screwed on all the way tightly. So you'll get a little bit leaking out the edge, okay? That's a leakage radiation, and leakage radiation isn't strong enough to create an image or to hurt you, really. It doesn't go very far, and it's just weak radiation. Okay, so now we've got a rudimentary picture here. Let's look at it in a better format. All right, so here we have it already all drawn out for you. We have the tube head here, and this is made out of lead, right? Outer casing made of lead. Then we have the glass vacuum tube on the inside here. Here's our leaded glass vacuum tube on the inside. We have our negative side of the tube, which is the cathode where the electrons are. We have the positive side of the tube over here, which is where the protons are. When we push the button to take an X-ray, we allow the electrons to leave the cathode, and they shoot over here towards the anode. But instead of uniting with the anode, it hits the tungsten target, okay, which is this piece right here is a tungsten target. There's its listing, which creates the radiation called photons. Photons are aimed at the portal or the opening, and what we have in place first is an aluminum filter. So here we have an aluminum filter in place first, and then a collimator. The collimator is a lead washer. The primary beam can come out, okay. What hits the patient's face, teeth, tissues, and so forth is secondary radiation. It bounces around for a while. It's called scatter radiation. Then we have leakage from a cone that doesn't fit correctly. And remember, this is called, oh, let me change my color so it looks, you can see it better. This is called a, sometimes called a cone, properly called a PID, position indicating device. And the collimator has to be the right opening size so that by the time the radiation hits the end of the PID, it's 2.7 inches in width. Now I just did the whole review again on one slide, and that's not what I meant to do. So I'm going to go through these really fast. So here I meant to just do one on each side. So the cathode, negative side right here. Anode, positive side over here. Electrons are the negatively charged particles of an atom that are released from the cathode, and they shoot over towards the anode when we push the exposure button. We don't want the electrons to unite with the protons, and so we put a piece of metal in the way. It's made out of tungsten. We call it the tungsten target. And the ray that's produced from hitting that tungsten target is called photons. Photons, this ray produced. Then we have two pieces of metal that are in the way before the radiation comes out of the tube head. The first piece of metal in the way is the aluminum filter. Okay, that aluminum filter allows strong radiation to go through, but the weak radiation will stay inside the tube head and just dissipate in there. The next piece of metal is your collimator, which is like a lead washer. And there's a hole in the middle. Again, it's lead, so radiation cannot go through the lead part, but there's a hole in the middle of it, which allows the strong radiation to come out. That strong radiation that comes out is called the primary beam. Central beam, main beam, central ray has lots of names, but primary beam is aimed at the patient. The collimator is, the width of the opening of the collimator is directly proportional to the length of your cone, or the PID, so that by the time the radiation hits the end of the cone, it is 2.75 inches wide. And make sure that you know that the PID, or the cone, is properly called the PID, position indicating device. That's this part right here that's aimed at the patient. All right, we've hit most of the hard, 75% of the hard part of this lecture, maybe even more than that. All right, so now we just need to review the 4 different radiation beams. Remember, there's the primary that's aimed at the patient, secondary bounces off, scatter bounces around, and then leakage, which comes from a cone that's not on tight. Okay? Which of those 2 would you say could potentially be harmful to you as the operator? Well, remember, the primary beam, or the primary radiation, is going to be aimed at the patient. That's not going to hurt you. I mean, unless you're really being silly and you aimed the X-ray head at yourself, you're not going to be hurt by the primary beam. Don't worry about that. But you could be hurt by secondary and scatter radiation, which is the radiation that bounces off the patient until it loses its energy, if you're within the harmful zone. 6 feet is the magic distance. X radiation cannot travel more than 6 feet. So as long as you are, and that's why they put the button outside of your operatory room. It's on the other side of a wall and at least 6 feet away, so that you're outside of where the radiation could be. Okay, so the 2 types of radiation beams that could be harmful to you as an operator are secondary and scatter. Now we have 2 concepts left having to do with the electrons and the speed of the electrons and the amount of electrons that are released from the cathode that gives us 2 different characteristics of our image. So characteristics of the electrons. The first term is contrast. Contrast, if you're contrasting 2 things, you're comparing them, right? And if they have a lot of contrast, that means there's a big difference. So if you have, you know, what's funny, the analogy that just came to my mind. Okay, you meet somebody new when you're going on a date, and they are very, very dissimilar to you. They don't have the same interests, same likes, or whatever. You have a lot of contrast. So that would be high contrast. So the difference in the degrees of blackness between adjacent areas on the same dental radiograph is contrast. So notice on this X-ray, you have some very, very white areas where we have amalgam filling, because the amalgam is very solid and radiation cannot go through it. And you have some very, very dark areas where we have air, we have no density. Very different between the black and white. So this is called high contrast. High contrast, very dark areas and very light areas on the same film. If we had low contrast is where we would not have a whole lot of really black and really white. We have more muted colors, which would be shades of gray. So notice here that the areas where there isn't any density is more gray than it is black. And the enamel of the tooth here is white, but it's not a solid, super dense white. So you have a lot more shades of gray here. So this would be called low contrast. Okay, not a whole lot of difference between black and white. Here's another picture illustrating the same thing. So notice here our high contrast means that we see lots of really white and lots of really black. In low contrast, everything is a shade of gray. Okay. What we actually want in X-rays is we want a healthy balance between high and low contrast. So we see some dark areas, some white areas, and lots of shades of gray in the middle. So you can actually see the ribs in this case. This is a lung. This is actually lung cancer. And you can actually see the ribs and the collarbone and so forth in this one, where you can't really make out the ribs or anything else on the high or low contrast because there aren't a lot of variations of gray. All right, so what creates the contrast on an X-ray? The contrast is created by the electrons. Remember, the electrons leaving the cathode when you push the button, and it has to do with how fast they're going, their speed. That is the KVPs, or kilovolt peaks. KVP stands for kilovolt peaks. The KVPs determines the speed of the electrons, how fast they're moving from the cathode to the anode. On your control panel, that's this number right here. We are at 60 kV. So again, going back to our diagram, what we're talking about is the electrons. And when we push the button to expose the X-ray, how fast are they coming out of the cathode? It is opposite. However many KVPs you have it set for, it causes the opposite effect. So low KVPs, so if you turn it down, the number low, it will give you high contrast. Don't worry about this term here, short scale. Don't worry about that. Low KVPs gives you high contrast. So let's look at these two pictures over here of a chicken wing. So we have this one here, which showing lots of black and white, very few shades of gray, and this one here, the opposite. Not as many black and white and a lot more shades of gray. Okay, so when we have low KVPs, we have a low setting, it's going to give us high contrast, which means it's going to give us more black and white. So we're talking about this one over here. Large differences in densities, good for diagnosing decay and abscesses. Notice with this picture over here, we can see the bone, what's going on with the hard tissues and the bone really well, much better than we can in this picture over here. When we set our KVPs high, so high KVPs will give us a low contrast. Okay, will give us low contrast. So high KVPs, this would be a high setting, is going to give us a lot more shades of gray. What that's good for is diagnosing periodontal disease. Okay, so if you look at this one, we can see the soft tissues and what's going on here with the soft tissues a lot better than we can in this picture here with high contrast. Okay, so just remember with KVPs, it's the speed of the electrons which determines the contrast, and its opposite effect. When you have low KVPs, it gives you high contrast. High KVPs, it gives you low contrast. All right, so let's just take a couple of pictures here and make sure we're understanding this. Which one is high contrast or higher than the other? Which of these two pictures is showing higher contrast? Hopefully you said B here. This one is higher contrast, has more black, white, and some shades of gray. Again, don't worry about this short scale, that you won't ever be tested on that. I shouldn't have included it. Now I've changed the question up here. Which one has higher KVPs? Not high contrast, but higher KVPs. Remember, opposite effect, hint, hint. Higher kVps gives us lower contrast. So A has more kVps, so more shades of gray and less contrast. All right, one more concept to go here, density, and we'll be done with probably the hardest of all of the podcasts. Your next podcast is on biological effects of radiation and radiation safety, and that also has some challenging concepts to it, but if you have survived this one, you will survive all of the rest. We started out with the hard ones, and we're going to smooth sail from here on out. Okay, so the last concept we're going over here is density. Now, when we're talking about density, we're talking about the film and comparing one film, how dark the film is in general, to another film, the overall blackness or darkness of a dental radiograph. So looking at these two images right here, which image would you say is darker overall? In general, which one's darker, left or right? Hopefully you said right. This one's darker. This one is lighter over here on the left. That is the density of the image. Now, is there a lot of contrast on either one of these two images? I'd say no. There's not a huge contrast on either of the images. The white areas aren't super white, and the black areas are not super black on either one of these, although the one on the right overall is darker than the one on the left, and that's what we mean by density. Now, I did put up here meaning number one of density because there's another concept of density I'm going to talk about right here. So when you're reading test questions about density, you need to make sure that you're understanding whether or not it's talking about density of the film in general or density of the object, which is meaning number two. So density of the film is the overall blackness or darkness of the image, and that is controlled by milliamperes. Milliamperes, or MAs, is what controls the amount of electrons. The amount of electrons. So again, go back to picture the tube head in your mind, and the cathode, the negative side where the electrons are sitting waiting to be used. When you push the button to expose the X-ray, we've already talked about the speed of the electrons going from the cathode to the anode. Now we're talking about how many electrons are released. The more electrons that are released, the more dense the overall blackness of the image. Again, here's our drawing, cathode, negative side, and notice I'm saying this a zillion times, so hopefully it's getting stuck in your head. It has the electrons. Remember, we already talked about the speed is controlled by the kVps is the speed of these electrons, which controls the contrast, right? Now we're talking about how many electrons are released, the numbers, the amount, or how many electrons are released. 1, 2, 3, a million, 1,000, however many are released. That controls the density of the image. On this one, I put controls the number of X-rays, which is sort of true, but it's better to say the number or amount of electrons moving from the cathode to the anode. And on your control panel, that is this right here. So notice it says 7 MAs. Again, the higher the milliamperes, the higher the number that you have this set to, the more dense the image will appear. So when the milliamperage is increased, the MAs are increased. So we're increasing the amount of electrons, and the density of the image is going to be higher. We then need to turn down our exposure time, how much time we're exposing the image. So notice that there are 3 settings on your control panel. There's the kVps, which controls the speed of the electrons and the contrast of your image. the MAs, which controls the amount of electrons and the density of the image, and then you have exposure time. On most X-ray control panels, they are set in such a way, and the manufacturer suggests that you do not change the KVPs and the MAs ever. The only factor that you really, as an operator, should change is the exposure time, because as you change that exposure time, the MAs and the KVPs then are proportional to the time of the exposure, and you want to make sure that you don't adjust one and then go adjust another one and then they all get kind of out of whack. So most units, most of the time, you won't be changing the MAs and the KVPs. Those are set by the people that inspect your equipment every 5 years, which we talked about before. You just are going to change the exposure time. Now think about that in terms of laying out in the sun, right? If you are out in the sun, and I've already used this analogy, I'm going to say it again. If you're out in the sun, the more intense the sun is, the less time you need to be out there to get a good tan, right? So if you have increased milliamperage, so the intensity of the sun is high, then you would want to turn your exposure time down, less intensity, okay? And again, MAs affects the density of the X-ray. The higher the MAs, the darker the image. All right, so just a quick review of the control panel. We have the on-off switch. You turn it on at the beginning of the day, turn it off at the end of the day. Okay. The control panel, or excuse me, the time control, which again, the exposure time. You have the milliamperage, which is the amount of electrons, which controls the density of the image, and the KVPs, which controls the speed of the electrons, and that controls the contrast. So here are your typical settings. If you have a short cone, so your PID or your cone is considered short, and that's 6 inches or so, 6 to 8 inches or so. These are the normal settings, 10 MAs and 70 KVPs. If you use a long cone, so your cone is quite a bit longer, and that's usually like 12 to 16 inches, then you need more MA or electrons and more speed of the electrons in order to get the same quality X-ray, because the electrons are going, the photons are going a further distance, right? So the longer the cone, we would increase the MAs and the KVPs. Use my analogy of throwing a ball. If I throw the ball 3 feet and I want it to hit the wall that I'm only 3 feet away from at a certain intensity, and then I back up 20 feet and I still want that ball to hit the wall at that same intensity, I better throw it a whole lot faster, right? And maybe even throwing a whole lot more of them would be helpful. So the further the cone, the longer the cone, the faster and the more electrons you need, you turn up your settings. Okay, now remember I said there was another time when we use the term density. There's another meaning to it. Sometimes we'll talk about the density of an object. So if an object is very, very dense, and this is not going to be news to you, we've talked about this before. So if you are taking an X-ray of some metal, for example, in the mouth, be it amalgam or a metal crown or a porcelain to metal crown with a metal underneath, metal is a very dense object. Radiation cannot go through it, and so it's going to show up white on the X-ray, and that's called being radiopaque, right? Radiopaque, showing white on the X-ray. If something is not dense, it's an airspace or it's fluid. In the case of an abscess tooth where there is infection, you can see this infection here. What actually happens is the infection eats the bone. So that's actually a hole in the bone now where the infection is. Since it's a hole, it is not dense. It shows up dark on the x-ray, and we call that radiolucency. So sometimes you'll see some test questions about the density, and what you want to make sure you're paying attention to is whether or not it's talking about density of the film, which has to do with the MAs, or density of an object, which will determine if it's radiopaque or radiolucent. All right, and we are done. We've used a whole bunch of new terms. All of these should be familiar to you. I won't go through each one of them right now. This might be a good review for you to see if you can write down each one of these and remember what it is referring to. I'm looking at a quick glance right here. I think the only two that I see we haven't mentioned is cumulative, and that is just referring to the fact that radiation that you receive in your body is cumulative. And there's a cumulative effect of radiation until your body has a chance to recover. And we're going to talk more about that in the next lecture, so I wouldn't worry about that right now. And then just the word distortion, and that word also probably doesn't need to go here in this list. Distortion just means if you take an x-ray and it doesn't look exactly the way it does in the mouth, that means it's distorted. Which we're going to talk about also in another lecture. But the rest of these terms here should all be familiar to you now. Double check yourself, make sure you know the meaning of each, and you will be good. Also check out the article, again, back on our website in the resources section for this class entitled Imaging Terms. It's really good. Phew, and I don't know about you, but I now need a nap. All right, next up, biological effects of radiation and radiation safety. I'll talk to you there. Don't forget to take your quiz.